So we simplify the augmented matrix to convert this into an upper triangular matrix and write a new system of equations, and that simplifies our task of finding the solutions. Okay. So this leads to the concept of row echelon form of a matrix. Yeah. So we consider general form of the coefficient matrix of the system of linear equations for which the method of back substitution works. So take a m by n matrix. A is a m by n matrix with real entries. A row is said to be 0 if its entries are all 0. Okay. The first non-zero entry from the left of a non-zero row is called the pivot of this row. Yeah. So if all the rows are 0, there is nothing to do. There are no non-trivial equations to solve. And if there is a non-trivial equation, that means some coefficient of some variable must be non-zero. Yeah. So we look at the first non-zero entry from the left of a non-zero row. So there is a non-zero row in the coefficient matrix. And look at the first non-zero entry from the left of a non-zero row. This is called the pivot of this row. Yeah. So every non-zero row begins with a few entries in that row could be 0, but then we encounter first time a non-zero entry in that row. That is called the pivot of this row. Yeah. So all the entries to the left of the pivot are equal to 0. So for example, look at this matrix A. It's a 3 by 3 matrix, and in the first row, the first non-zero entry is 1. The second row is a 0 row. The third row, the first non-zero entry is 5. Okay. So 1 is the pivot of the first row, and 5 is the pivot of the third row, and the second row has no pivot. Yeah. So we identify the pivots in every non-zero row. So the number of pivots is equal to number of non-zero rows in the matrix. Okay. So a matrix is called is said to be in row echelon form if and only if the non-zero rows of A precede the 0 row of A. So all the 0 rows should be pushed to the bottom. Yeah? All the 0 rows are at the bottom of the matrix in row echelon form, and so the non-zero rows are on above the 0 rows. So if A has non-zero rows and the pivot in row 1 appears in the column K1, and then the pivot in row 2 will appear in column K2, and so on, then the column indices should increase. So if K1 is the first column in which the first pivot occurs, and K2 is the second column in which the second pivot occurs, then K1 is less than K2. Okay. So if first pivot occurs in certain row in some column, the second pivot will be to the right of the first pivot. The third pivot will be to the right of second pivot, and so on. So this is the condition that K1 is less than K2 is less than Kr. So for example, this matrix, this 3 by 3 matrix, this is in row echelon form. Yeah? Because the first row has first non-zero entry, that is the pivot 5, and the second row, the pivot is 1, and it is to the right of the first pivot. And third row has no pivots. So pivots are sliding to the right. Okay? And the 0 rows are at the bottom. Then we say the matrix is in row echelon form. But if you look at these 3 matrices, they are not in row echelon form. Look at the first matrix. The pivot in the first row is 1. The pivot in the last row is 5. And this 5 is not to the right of 1. Similarly, the second matrix is not in row echelon form, because the second pivot is to the left of the first pivot. And third matrix is also not in row echelon form, because we want the second pivot to the right of the first pivot. And in this case, it happens to be just below the first pivot. So they are not in row echelon form. Yeah? So row echelon form, a matrix is in row echelon form. First condition is all the 0 rows are at the bottom of the matrix. And now you look at the non-zero rows. Every non-zero row has a pivot. So that is the first non-zero entry in any row. So look at the first row, and first row, if it is non-zero, it has a non-zero entry. That is the pivot in the first row. Now look at the second row. this will, if it is non-zero, then it has a non-zero entry, and the first non-zero entry in the second row should be to the right of the first non-zero entry in the first row. Yeah. So we say the second pivot is to the right of the first pivot. Similarly, third pivot is to the right of second pivot, and so on. Then the matrix is in row echelon form. We will see that if a matrix is in row echelon form, the coefficient matrix of a system of linear equations in row echelon form, then it is very easy to solve that system by back substitution. What we did for an upper triangular matrix, where all the entries on the principal diagonal were non-zero, we could solve that, and there was a unique solution. But when we have a yeah, so every upper triangular matrix is in row echelon form. No, it's not true. Look at the third matrix. Yeah, third matrix here. This is upper triangular, but it is not in row echelon form. Yeah, the condition for row echelon form is that the pivot should slide to the right. Yeah, first pivot. Then look at the second pivot. Second pivot should be to the right of the first pivot, and so on. In this third matrix, which is in upper triangular matrix, the second pivot is just below the first pivot. We don't want that. The pivot should move to the right. As we go down from first row to the second row, the pivot should be to the right of the first pivot. Okay? Yeah. So, pivotal columns. So if a matrix in row echelon form, the pivots are sitting inside certain columns. So for example, this first matrix here, which is in row echelon form, 3 by 3 matrix, the pivots are sitting in the first column and the second column, and the third column has no pivots. So pivotal columns are first and the second column, and the third column is a non-pivotal columns, right? So number of pivotal columns is equal to number of pivots in the matrix, and number of pivots is equal to number of non-zero rows in a matrix in row echelon form. So if a matrix has is exactly R non-zero rows, and if it is in row echelon form, then it has exactly R pivots, because every non-zero row will give rise to a pivot. So number of if it is in row echelon form, okay, the number of pivots is exactly the number of non-zero rows. Yeah. Somebody opened the mic, I think. Yeah. Just a minute. Yeah. Okay. So a column of A containing pivot is called a pivotal column. So therefore, there are R pivotal columns, and R is at most the number of rows and the number of columns, because the pivots are sitting in certain columns, and number of pivots cannot exceed number of columns, and number of pivots cannot exceed the number of rows. Yeah. So if there are R pivotal columns, then R is at most n, and R is also at most m. So let us look at an example of back substitution when the coefficient matrix is in echelon form. Yeah. So A is this matrix, and look at the second column, fourth column, and fifth column. These are the columns in which the pivots are sitting. So I am assuming that A12 is non-zero, A24 is non-zero, and A35 is non-zero. And the zero row is at the bottom. Yeah. So there are 3 pivotal columns, and there are 3 non-pivotal columns. There are 6 columns. So every column is either a pivotal column or a non-pivotal column. And the number of non-zero rows is number of pivots here. And we write the coefficient matrix and the vector B. So at the back of this, we have the system of linear equations AX equal to B. Yeah. So these are the pivots, and pivotal columns are second, fourth, and fifth. And suppose so there are 6 columns, and there are therefore 6 variables. And so the system of equations is AX equal to B. And look at the last row. The last row corresponds to the equation 0x1 plus 0x2 plus 0x6 equal to B4, right? So if there is a solution, then B4 is forced to be 0. Yeah, because no matter what exercise you put, this equation will say that if B4 is not equal to 0, then there is no solution. Yeah? So if B4 only then there is a solution. So this is a if the coefficient matrix is in row echelon form and B4 is non-zero, then we can right away stop and say that this is an inconsistent system of linear equations, and B4 is because B4 is not 0. So if B4 equal to 0, then let us see that there is a solution. Okay. In fact, there will be infinitely many solutions. Let us see how it is. So, assuming that B4 is 0, we look at the equation corresponding to the third row. The third row, the equation corresponding to third row is A35x5 plus A36x6 equal to B3. Okay. So this equation can be solved by writing x5 as B3 minus A36x6 over A35. Yeah, A35 is not 0 because it's a pivotal entry in the matrix, but x6 is corresponding to sixth column, and sixth column has no pivot in this. Yeah, so we can determine x5 by any value we substitute for x6, right? So x5 will be determined once I know the value of x6, but we give arbitrary value to x6 and I will get the value of x5. Okay. So to find a particular solution of ax equal to b, we normally put x6 equal to 0. And that will say that x5 is b3 over a35. But any value of x6 can be given to get the value of x5. So x6 is a kind of free variable because we can substitute any value to this unknown quantity. Okay. Yeah. So next we go to.
Excuse me, sir. There's a question from Anirudh. He says that is it true that REF exists for every upper triangular matrix?
REF exists for any matrix. Yeah, there is a procedure called Gauss elimination method, which will convert a given matrix into row echelon form. Okay. So this system of linear equations I have taken deliberately in row echelon form. Yeah. By using row operations, we have brought the coefficient matrix into row echelon form. I will describe the method. In an example, I gave the method already, but we will formalize this. Right now, we have a system of linear equations where the matrix is in row echelon form. Okay, so x6 is a free variable. I give any value to x6 and get value of x5. And now move on to the second equation. The second equation. The second equation is A24x4 plus A25x5 plus A26x6 equal to B2. So I can solve for x4 because I know x5 and x6. x5 was determined by giving a value to x6. So the indeterminates which are corresponding to the pivotal columns. So in this case, they are x2 and x4 and x5. So these are determined by giving values to the variables which are corresponding to non-pivotal columns. Yeah. So x4 is determined once I know the value of x6 and x5, but x5 was determined by an arbitrary value of x6. So we can find out x4. Yeah. Then we substitute these values of x5 and x6 to find x4. And finally, we look at the first equation. In the first equation, the second equation, there was no x1 and there is x2. The second column was a pivotal column and a12 is non-zero, and therefore I can write x2 in terms of x3, x4, x5, x6 and substitute these values. Yeah. So here x5 and x6 were already determined, x4 was determined, but x3 we did not determine, right? Because x3 corresponds to a non-pivotal column. The third column is a non-pivotal column, and any value to x3 can be given to find out the other values. So x2 in the equation for x2, x4, x5, x6 values are determined, and the x3 can be given arbitrary value, and x2 is determined. So there was a question just now.
Yes, sir. So the
Yeah.
question is by Megha, and she asks, can we assign any value to unknowns of all non-pivotal columns?
Yes, that's what I'm driving at, that the pivotal columns, the pivotal variables have non-zero coefficient in front of them. So they can be solved by dividing by the coefficient of those pivotal variables. The non-pivotal variables can be given arbitrary value. Okay. So I'm just explaining in this example, but this is the general picture. We will come to that. So x2, as you can see in x2, x6 was a non-pivotal variable, so we gave arbitrary value, but x5 was corresponding to a pivotal variable, and so that value was determined from the value of x6, and then x4 value was determined from value of x5 and x6. x4 correspond to a pivotal column. x3 was not a pivotal column, so we didn't solve for x3 because a13 could be 0. I didn't circle a13, it was not a pivot. a13 could be 0, right? So x3 can be given any value we want, but x2 was corresponding to a pivotal column because a12 is non-zero, and that is the first non-zero entry in the second row. So I can solve for x2, yeah, and so this is what I said. We can assign arbitrary value to the variable x3 because it is corresponding to a non-pivotal column, and back substitute to get values of x4, x5, x6, and x1 can also be assigned arbitrary value because it is a non-pivotal variable. Yeah, we don't know whether a11 is 0 or not. Yeah. Okay. So the variables x1, x3, x5 are corresponding to x1, x3, x6 can be assigned arbitrary values corresponding to non-pivotal columns 1, 3, and 6. They are the free variables because we can assign any values to them. So suppose I have a matrix which is in row echelon form, and there are R non-zero rows. So there are R pivots. And so the R pivots are, suppose they are in the K1 column, K2 column, and K3 column. These are the column indices, right? First pivot occurs in the K1 column, second pivot occurs in K2 column. So the condition for this matrix to be in row echelon form is that K1 should be less than K2, less than KR. And this condition says that the second pivot is to the right of first pivot, the third pivot is to the right of second pivot, and so on. Yeah. So, and the remaining columns are non-pivotal columns. So they have certain, suppose L1, first non-pivotal column is L1. So for example, in the previous example, the first column itself was a non-pivotal column. Therefore, L1 is 1. Yeah. So L1 is 1. So in that example, the non-pivotal columns were 1, 3, and 6. There are 3 non-pivotal columns in that example. So the values of L1, L2, L3 are 1, 3, and 6. Yeah. So the columns are classified into 2 varieties, the pivotal columns and non-pivotal columns. And you simply find out the column numbers. And these are these values, K1, K2, KR. They are the column numbers of pivots. And L1, L2, Ln minus R. If R there are R pivots, then there are Ln minus R non-pivotal columns. And you write which are the non-pivotal columns. So non-pivotal columns are L1, L2, Ln minus R. So the pivotal variables are in the K1, K2, KR columns. So xk1, xk2, xkr, they are the pivotal variables. They are determined in terms of the non-pivotal variables. Non-pivotal variables are the free variables. So the free variables, we are denoting them by xl1, xl2, xl, and minus r. Okay. Yeah. So don't be afraid of this notation. We are simply writing the column numbers where pivots are occurring, and just writing the variables corresponding to the columns in which pivots are occurring, and they are xk1, xkr. These are the pivotal variables, and remaining variables are free variables. And the previous example suggests that the free variables can be given any value we want, and the pivotal variables are dependent on values of free variables. We have no control over the values of pivotal variables. They are determined in terms of the values of the free variables.